Welcome back, students. Here we're going to be looking at section 11.5, which is about finding the probabilities of independent and dependent events. So let's start with some definitions. We say that two events are independent if the occurrence of one event has no effect on the occurrence of the other event. So for an example, we might talk about tossing a coin twice, where if I toss the coin the first time and I get heads, that result doesn't have any impact on what will happen when I toss the coin a second time, right? It's still going to be 50-50 chance of coming up heads or tails. And now you might think, oh, well, aren't all events independent? Well, the answer there is no. There's lots of situations where events are dependent. We say two events are dependent if the occurrence of one does have an effect on the occurrence of the other. So an example of this could be drawing cards from a deck of cards where we're not replacing the cards in between our draws. So if we want to take the probability of, say we're drawing two cards from a deck and not putting the first card back after we draw the second one. When we draw that first card, it's like there's 52 possibilities, right? But with that first card still in our hand, when we go to draw the second card, there's now only 51 possibilities for that second card. So the probability there is changing just based on the fact that I've pulled one card out of the deck. So in situations where you're removing something where you're choosing things from a pool, from a group of objects, and you're removing them, those are situations where the probability will be conditional. And then almost all like real life situations, the probabilities are going to be dependent. So like, you could look at things like, gender and favorite sport or something. And like, it turns out that if you try to measure this empirically, there may be some kind of relationship between, some kind of an effect that the gender of, the individual might have an impact on what kind of sport is their favorite or something like this. So there's lots of things kind of in the real world that might seem unrelated, but there might be some effect on the two events there. So let's talk about how we compute the probability then. So if we have two events that are independent, the probability that both A and B occur is just the probability of event A and B is equal to the probability of event A times the probability of event B. That's pretty straightforward. If A and B are independent, then the probability that both events A and B occurs, the probability of A and B is equal to the probability of A times the probability of B, given that A has already occurred. So that's how we read this symbol here. So that's the probability of B, and then the vertical line there stands for given that, we'd say event A has already occurred. So we call this guy a conditional probability. Okay. So let's do some examples now to kind of get the feel for how we use these formulas. Keep in mind, the first thing that I'm going to be doing on each of these problems is trying to identify whether the two events are independent or dependent. So really throughout all of these problems or all of these examples, I need to be thinking to myself, what are the two events? And then based on what I know about the two events, are they independent or dependent? So the first example says a raffle has sold 150 tickets for a bicycle and 200 tickets for a television set. So we're going to draw a ticket out, and the person that has the winning bicycle ticket is going to win the bicycle, and the person that has the winning TV ticket is going to win the TV. So it says we buy 5 tickets in each lottery, and we want what is the probability of winning both prizes. So one event here is going to be winning the bicycle. The other event is going to be winning the television set. Now, are these two probabilities independent or dependent? Well, since we have a separate ticket and a separate drawing to win the bicycle, and a separate kind of ticket and a separate drawing to win the television set, these are going to be independent. If we just sold 150 tickets and there are 2 prizes, a bicycle and a television set, there is a situation where they would be dependent. But because we have a separate pool of tickets for the bicycle and then a separate pool of tickets for the television set, these are going to be independent events. So here's my event A, here's my event B. This is independent. Oops, let's write it here. So since it's independent, the probability of A and B is equal to the probability of A times the probability of B. So the probability of winning the bicycle, well, I have 5 bicycle tickets out of 150. And I have 5 TV tickets out of 200. So that's really it. When I multiply this out and reduce my fraction, I get 1 out of 1,200. Okay. So the probability of winning only the bicycle. So this is a conditional probability, right? We want the probability of winning the bicycle given that we have not won the television set. Or I'm sorry, it's not. I don't want to say it as a conditional. I want to say and not winning the television set. Okay. So, again, these are independent events, right? Because the result of A has no effect on the result of B. Remember that this B with the bar over top, that's a complement. We talked about that in the previous lesson, right? That's the same thing as not. So the probability of A is, again, 5 out of 150. And the probability of not B, well, 195 of those tickets aren't yours. Over 200. So again, if I type this into my calculator, I have 5 for 150 times 195 over 200. So I get 13 out of 400 there. Okay. The probability of winning only the TV set, so I don't want to win the bicycle, but I do want to win the television. And again, still independent. So to not win the television, well, there's 145 tickets that aren't mine. And then P of B is still the same as up there. So that gives me 29 out of 1,200. Okay. So here asks for the probability of winning the bicycle or the television. Well, there's three possible outcomes here if I want the bicycle or the television. I can win the bicycle only, I can win the television only, or I can win both the television and the bicycle. So if you notice, that's exactly what we computed in these three steps: bicycle and television, bicycle only, television only. So I have really just 1 out of 1,200 plus 13 out of 400 plus 29 out of 1,200. So when I do that, I get 23 out of 400. Okay. And then we have the probability of not winning any prizes. So that's the probability of not A and not B. So again, these are independent. So I have 145 out of 150 and then 195 out of 200. And that gives me 1,131 over 1,600. Okay. Let's move on to another example. It says, in a race, each heat consists of 8 competitors who are randomly assigned the lanes 1 through 8. What is the probability that a competitor is assigned lane 8 in each of the 3 heats that they compete? So here we have 3 events going on. We have heat 1, we'll call that event A. Heat 2, we'll call that event B. And then heat 3, we'll call that event C. So we want the probability of lane 8 and getting lane 8 again, and then getting lane 8 again. The question becomes, are these lane assignments for these 3 heats independent or dependent? Well, is there anything in the problem that would indicate to you that your lane assignment in heat 1 would have any effect on your lane assignment in heat 2? No, right? Because in each heat, we're assigning all the lanes randomly. So this is independent again. So just the probability of getting lane 8 times the probability of getting lane 8 times the probability of getting lane 8. And since these lanes are randomly assigned, it means we have an equal chance of getting lane 8 in each heat. And since there are 8 lanes total, getting lane 8 is just a 1 out of 8 chance. Again, there's only one lane 8. That's why there's a 1. And then the number of lanes, well, I have lane 1, I have lane 2, I have lane 3, I have lane 4, I have lane 5, I have lane 6, I have lane 7, I have lane 8. So there's 8 choices total. So I have a 1 out of 8 chance of getting lane 8. So when I do that, I get 1 out of 512. Okay. Let's look at another example. The table below shows the number of tropical cyclones formed during hurricane season. So we have the type of cyclone. So there's depressions, storms, and hurricanes. And then the locations, northern hemisphere and southern hemisphere. So if I look at this right away, I can see that this is a dependent situation where the type of storm or the type of cyclone is dependent on the location, whether you're in the northern or southern hemisphere. So the first question asks, what is the probability that a future tropical cyclone is a hurricane? Okay? So if I do that, I'm going to basically just count up the number of hurricanes. So if I do that, I have 545 plus 215. Those are my number of hurricanes. And I should be dividing by the total number of tropical cyclones. So the cyclones are all of these. So I'm going to have 199 plus 18 plus 398 plus 200 plus 545 plus 215. So when I do that, I get 760 over 1575. And this comes out to be about 4.83. Or I'm sorry, 0.483. Okay. Now, why didn't I use my conditional or, I'm sorry, my independent or dependent probability formulas? Well, because this wasn't an and statement, right? What is the probability a future tropical cyclone is a hurricane? It didn't have an and in there, right? We're not looking at two events happening. There's just one event. Is it a hurricane or not? Oh, okay. That's fine. In the next question, it asks, what is the probability that a future cyclone in North America or in the northern hemisphere is a hurricane? So this is a conditional probability. We want the probability that we're getting a hurricane given that we're in the northern hemisphere. Okay, so to do that, what I'm going to need is the number of hurricanes in the northern hemisphere only divided by the number of cyclones in the northern hemisphere. So that gives me 545 over 1142, which is about 0.477. Again, I knew that this was not a independent or dependent event thing. Again, there's no and in that statement, right? It says, what is the probability that a future cyclone in the northern hemisphere is a hurricane? So there was no and in that, so it's not an independent or dependent event situation. It's just a probability. Now, this particular probability is conditional, right? So we have the probability of event A given that it's in event B. So I wanted the probability of a hurricane divided, or in the northern hemisphere, right? So if we have probability of A given B, that's the probability of A and B divided by the probability of B. So here I have a probability of a hurricane. The tropical storm is a hurricane and it's in the northern hemisphere. That's the 545. And then the probability that it's a hurricane, or I'm sorry, probability it's in the northern hemisphere is all of the northern hemisphere stuff. Okay. So again, maybe we should have written this down back when we had the formula. It's just, or when we defined this. Way back up here. When we defined a conditional probability, maybe we should have included that formula there. Okay, let's look at another. Here it says you randomly select 2 cards from a deck of cards. What is the probability that the first card is a heart and the second card is also a heart, given that you replace the first card before you select the second card? So we're doing the probability of a heart and then another heart. So this is, I need to decide whether these are independent or dependent events. So the thing that's going to tell me that is that it says you replace the first card before you select the second card. So when I draw up that first card, it's an out of 52. When I draw the second card, it's still out of 52 because I've put the first card back. Okay, so this is independent. So I'm just going to have the probability of drawing a heart times the probability of drawing a heart. So how many of any suit is there in a deck of cards? 13 out of 52 total cards. And since I put that card back in, there's still going to be 13 hearts and 52 cards when I do that. So this gives me, when I reduce the fraction, 3 out of 16, or about 0.188. The second one says that we do not replace the first card. So this, again, still the probability of drawing a heart and then another heart. But here, this is going to be dependent because we're not putting that card back. Okay. So this is going to be dependent. So the first heart, still 13 out of 52. But now, to draw that second heart, there's only 12 hearts left because we already pulled one out. And there's only 51 cards total because we've taken one card out. So when I do that, and I multiply this out and reduce, I get 13 out of 68, which is about 0.1 or 0.191. Okay. And here's our last example, and this one is probably the most complicated. Let's read it first, and we'll talk about how I'm going to go about doing this. So it says, using observations made of drivers, a study reports that 69% of adults wear seatbelts while driving. A high school student, also in the car, wears a seatbelt 66% of the time when the adult wears a seatbelt, and 26% of the time when the adult does not wear a seatbelt. What is the probability that a high school student in the study wears a seatbelt? Okay, so what we're going to do is we're going to draw something called a tree diagram. So there's two situations. The probability that the adult wears a seatbelt we have is 69%. I'm going to write as a decimal, 0.69. And then the probability the adult does not wear a seatbelt then is just going to be 1 minus 0.69 or 0.31. It then says a high school student also in the car wears a seatbelt 66% of the time when the adult wears a seatbelt. So the probability the high school wears a seatbelt given that the adult wears the seatbelt is 0.66. So the probability the high school student does not wear a seatbelt given the adult wears a seatbelt is 0.34. It says then, and the high school student wears the seatbelt 26% of the time when the adult does not wear the seatbelt. So this is another conditional probability. So the probability the high school student wears his seatbelt, given that the adult does not, is 0.26. And the probability that the high school student then does not wear its seatbelt, given that the adult does not wear its seatbelt, is going to be 1 minus 0.26 or 0.74. Okay, so we have our event A going on here, which is whether the adult wears its seatbelt or not. So we say 0.26 or 0.69 is yes, and 0.31 is no. And then our second situation, our event B, is whether the high school student wears its seatbelt or not. So when the adult wears their seatbelt, the high school student wears their seatbelt 66% of the time, and it does not 34% of the time. And then if the adult does not wear their seatbelt, oops, got to write the 34% there. The high school student wears their seatbelt 26% of the time, and they do not wear their seatbelt 74% of the time. So if I'm looking for what is the probability that the high school student wears their seatbelt, there's two outcomes in this tree diagram that I've drawn where the high school student is wearing their seatbelt. So we have two situations. I have two paths through this tree to calculate. I have this path, and then I have this path. Okay? So I have for the first path, I have the probability of A times the probability of of H given A. Right? So that's the probability of A and the probability of A given H. So it's 0.69 times 0.66. And then for this other path, I have the probability of not A times the probability of H given the probability of not A. So that's 0.31 times 0.26, and then I'm just going to add these two up. So when I do that, I get 0.536. And that's the percent of time, or the probability that the student wears their seatbelt. So again, what I did here was I did 0.69 times 0.66 plus 0.31 times 0.26. And there's my 0.536. So in a situation like this where you're given some conditional probabilities like this, you'll want to write out what those conditional probabilities are and really draw a tree diagram. It makes life much, much easier when you have that tree diagram drawn, because now all we're doing is just kind of multiplying along the paths that you're looking for. And in our case, since we were concerned about high school student wearing their seatbelt, we were just looking for the paths that end in a yes situation. We'll do another exam, or you'll do another problem like this in your homework. When you do that, I would refer to this as it's a good kind of scaffolding for you to, to base your work on. But this should be enough for you guys to be able to do your assignment. So good luck, and we'll see you again later.